Hello viewers and subscribers of this channel. In this video I will explain you how to solve constraint optimization problems in Python by using SciPy library and minimize function. Those of you who watch these videos and who follow my work know by now that while preparing these lectures I like to go an extra mile. That is, I always create a post that nicely summarizes everything that I will explain in the video. So here's the post, and this post contains all the equations and explanations, and in addition it contains Python codes that can be seen over here. A link to this post is given in the description below. Also, before I start, I would like to mention the following. It took me a significant amount of time and energy to create this video and this post. And consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. Okay, so let's start. In my previous post and video tutorial, which can be found over here, that is, if you click over here, I explained how to solve unconstrained optimization problems by using the SciPy library and minimize method. In this video, I will continue with the explanations and I will explain you how to solve the constraint optimization problems. I have to mention that the implementation of the constraint optimization problems is a little bit more complex compared to unconstrained problems. Consequently, this video and this post is a little bit longer. In this video, we will use a very popular approach for solving constraint optimization problems. We will use the trust region constraint method for solving minimization problems. This method assumes that the optimization problems are given by the equation number 1. In equation 1, x is the n-dimensional vector of optimization variables. Then f of x is our cost function. These three bounds represent the constraints. BL and BU are the vectors of lower and upper bounds on the optimization variable x. Then CL and CU are the vectors of lower and upper bounds on this linear term L times x. Here L is a matrix and, as I explained previously, x is the vector. This compact notation over here represents a set of L linear less than or equal to constraints. Then DL and DU are the vectors of lower and upper bounds on the nonlinear vector function g of x. So g of x is a nonlinear vector function mapping n-dimensional real space into p-dimensional real space. And this is the compact notation. So this notation represents a set of p nonlinear less than or equal to constraints. Let us now briefly discuss this optimization problem. First of all the less than or equal to inequalities should be interpreted element-wise. For example, if you see something like this, this is actually a shorthand notation for something like this. So what happens over here, we take BL1, BL2, we put these two quantities in this vector BL, we similarly take BU1, BU2, we put them in a vector, and as the result we obtain this constraint over here. Next, the one-sided less than or equal to inequalities of the form given by the equation number 6 should be formally written by the equation number 7. So what is the catch over here? Here x doesn't have a lower bound. However, in order to formulate the optimization problem and in order to enter this optimization problem such that Python can understand it, we need to have a formal lower bound. In this case, a lower bound is given by this vector BL, and every entry of this vector BL is minus infinity. Of course, we can use another trick for specifying the vector BL. So we can basically specify the vector BL as follows. So the trick over here is to select entries of the vector BL as large negative numbers. In this case, I chose minus 10 to the power 6. However, I still prefer the first option for specifying the vector BL, and the reason is the following one. Python will allow you to directly specify entries of the vector BL as minus infinity. In Python, minus infinity is equal to np dot inf, where np is an abbreviation for NumPy library. Before we explain the Python code, let us first explain how to transform particular problems in the general form. Consider this optimization problem. Here's the cost function. x1, x2, and x3 are scalar optimization variables. y1, y2, and y3 are constants, as well as these terms over here, a, I, j, and these constants are given in this matrix A. Now, let us for the time being forget the constraints. And let us pretend that these constraints do not exist. This cost function over here is basically a least squares cost function, and this problem is a least squares optimization problem. However, with these constraints over here, this problem becomes quite complex. And let us see how to transform this problem in the general form. First of all, by using the vector and matrix notation that's given over here, our original cost function can be written in the vector matrix form given over here. Here, this notation denotes the vector 2 norm. Okay, that was easy. How about the linear and nonlinear bounds? So let us analyze this bound over here. I claim that this bound can be represented in this vector form. And it's very easy to see that because if you remember, this symbol is applied element-wise. So what do? We take minus 5 from here, we put it over here. Then we take minus 5 from here, we put it here. And we take minus 5 from here, we put it over here. Similarly, we take x1, x2, and x3, we plug them in this vector, and we take the right-hand side, 5, 5, and 5, and we group the right-hand sides in this vector. That was easy, right? Okay, so let us proceed. How about the constraint that we can see over here? So these two bounds. Here's the trick. We basically have two inequalities. We take minus 3 and minus 20 and we put them here, minus 3 and minus 20. Similarly, we take the right hand side, we take 10 and 20 and we place them over here. And then by using simple matrix vector calculations, we can show that basically this term over here, that is equal L times the vector x, is equal to these middle terms, the term over here and the term over here. You can simply multiply the first row of this matrix by this vector, and let's do that. Minus 1 times the x1 plus 2 times x2 minus 5 times x3, and you get precisely the term over here. And by using the same principle, we can transform this nonlinear inequality in the form that you can see over here. Notice over here that I use the trick for specifying the bound when you only have one-sided inequality. So here I formally placed minus infinity to define a lower bound. Okay, now we're ready to explain the Python code. As you can see, I'm using the Spider Python environment. This environment is very convenient. It reminds me of MATLAB because you can simply select over here the code block that you want to execute. You do the right click and you basically click over here, or you press F9 and this block is executed. Let us first erase our Python workspace by clicking over here and clicking on yes. Okay, the first step is to import the necessary libraries and functions. We import NumPy, we import SciPy, and from SciPy we import minimize, bounds, linear constraint, and nonlinear constraint functions. Next, I will define a random matrix A, that is our data matrix. So going back to our code, here's my matrix A, here's my vector Y, and I need to define them. I will choose them as random matrices and random vectors. So I use numpy.random rand n, and I specify the matrix dimensions. In my case, I'm selecting 3 by 3 matrices, so I will have 3 optimization variables. And in the same way, I define my vector y. The next step is to define the cost function. Here's our cost function. It's a least squares cost function. So to define the cost function, I need to define a Python function. I will call this function cost function, and the first argument of this function will be the vector x. Note here that this is basically a row vector. And the second argument is my A matrix, and the third argument is my Y vector. And over here I compute the error, and I compute the 2 norm, and I square the 2 norm and return the squared 2 norm of the error. So for the given value of the vector x and for the given value of my A matrix and Y vector, this cost function will return the value of the cost function. The next step is to define the bounds. First, we will define the bound over here, this bound. So to define this bound, we will need to specify a lower bound and the upper bound. Now, notice here that I'm using different values for the lower bounds and the upper bounds compared to the bounds that I used in my post. Don't be confused about that. I'm using different bounds in order to make this code as short as possible and in order to define the basic principles. So once I define these two bounds, and I can evaluate them to show you how they look. So this is the lower bound. You can see the infinity trick. So I'm able to specify a lower bound as a vector containing infinity values, and my minimization function will perfectly understand this, and this is my upper bound. Now I will call the function bounds that is imported from the SciPy optimize. The first argument will be the lower bound, the second argument will be the upper bound. Next, I need to define the linear constraints. Going back to my post, I need to specify these constraints. I need to specify the lower bound, the upper bound, and this matrix over here. So let's do that. First, my lower bound will be defined like this. Here's the lower bound. Again, I'm having infinity, 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 minus infinities, and my upper bound is defined as follows. I need to just execute these two code lines, and here's my upper bound. It's 30, 30, 30. Again, I'm using different values compared to values that are shown over here, so don't be confused. The principle is the same. Now I need to specify my matrix, and in this case I will also assume that this matrix L over here is a random 3 by 3 matrix. And once I specify the lower bound, the upper bound, and the matrix cell, I can call this function linear constraint that's imported from SciPy optimize to formally define these constraints. The first argument is the matrix, the second argument is the lower bound, and the third argument is the upper bound. Let us now define the nonlinear constraints. Basically, we need to define this function over here, g of x, the lower bound, and the upper bound. So let's do that. Basically, first we need to define lower bound. The lower bound in this case will be equal to 0. The upper bound will be equal to 100. Notice over here that I formally introduced inaccuracy over here. This bound should be actually equal to 0. Why? Because this term over here is always positive. So this term over here is not the smallest, or actually better to say, not the largest lower bound, because 0 is the true bound. And I corrected that in my post over here. That's why my lower bound is equal to 0. The upper bound is equal to 100, and here's my function g. It is simply a sphere in 3 dimensions. So for given x, row vector, I take the first entry x1, I square it, then I add the second entry, I square it, and then I add the third entry and I square it. And finally, I can define my nonlinear constraints by calling this function that's imported from SciPy optimize. And by executing this code block, I define my nonlinear constraints. The next step is to select the initial guess of the solution. The question is, why do we need an initial guess? And the answer is the following one. We're using an iterative method to solve this optimization problem. And all the iterative methods need to be initialized. So we need to select a proper value of our optimization variable that serves as initial guess. In my case, it will be a random variable. Now, we will be using the optimization solver whose symbol is given here, or abbreviation trust constraint. This is actually trust region constraint method, and again its abbreviation is trust constraint. Often it's a good practice to see all the possibilities for specifying different options for the particular solvers. We can see these options by simply executing this code line. And here's the information. It's quite lengthy explanation, and it's always a good practice to read the explanation. So here are the parameters that we can specify. There are certain tolerances in solution, barrier tolerances. You can specify even sparse Jacobian. You can specify Hessian matrix. You can specify different parameters such as number of iterations, number of function evaluations, etc. However, to make this video as short as possible, I will not play with the parameters. I will just use the default parameters. However, I had to explain you this such that you become aware of this, because sometimes your solver might produce an inaccurate result, and then to deal with that problem you would either need to increase the number of iterations or the number of function evaluations. And finally, let us call our optimization solver. We'll be using the minimize function, and this function is imported from SciPy optimize. The first argument of this function is our cost function. So here's our cost function, and it's defined over here. The second argument is the initial guess of the solution, that's defined over here. The third argument is the used method. In our case, it's this trust region constraint. The fourth argument contains a list of constraints. They are linear constraints and nonlinear constraints. Note here that the bounds will be defined separately. This argument over here represents basically arguments that are directly sent to our cost function. So our cost function, besides the vector x, should receive the A matrix and Y vector, and we have to make sure that these arguments are properly specified. Then we use options. We basically use just standard options. This is basically a dictionary. You can also change these options by introducing maximum number of iterations, maximum number of function evaluations, etc. And finally, we specify our bounds. Bounds are equal to bound data. Okay, so let us execute the complete code and let us see the result. Basically, this function minimize returns the structure called result. And this structure and its objects or its entries can be very useful to diagnose the solution process. For example, you can see over here some parameters, some tolerances. You can see function evaluations, number of iterations, is the process successful or not, status, optimality, etc. All these parameters are very important for diagnosing the convergence and possibly identifying some problems that can appear. However, for us, the most important entry in this video is the entry over here, and that's our solution. So basically, we can access this solution by typing result.x, and here's our solution. It's a vector of 3 entries. Okay, that would be all for today. I hope that you liked this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.